Hello everyone, welcome to another video from the tutorial series Aspen Plus Mastery and Certification. My name is Tabish. In this video, we will learn how to define the specification of a process stream. We will consider a process stream that has conventional components as well as solid components and how to simulate mixer, flow splitter and substream splitter. These three units are available in the mixer splitter palette in the simulation environment of Aspen Plus. So let's consider following case study for today's discussion. In this example, two feed streams named as F1 and F2 are mixed together to produce a mixed stream with the name as MIXP. The flow rate, temperature and pressure of both of these streams is the same. Both of these streams have air and solid entrainments, where air is considered as 79% nitrogen and 21% oxygen, flowing at a rate of 9,990 kg per hour, and solid is simulated as alumina and carbon graphite, each of them flowing at a rate of 5 kg per hour. The composition, along with the temperature, pressure and the total flow rate of the F2 stream is also the same. However, both of these streams differ in the particle size distribution, whereas the particle size distribution of F1 can be modeled as standard deviation of 2 micrometer with a median particle size of 6 micrometer, whereas in the F2 stream, the median particle size is 14 micrometer. So after mixing, both of these streams, a part of the mixed stream is diverted to the solid separation unit, whereas the other part of the mixed stream is sent to another downstream processing unit. As of now, no information has been provided about the downstream processing of the FSP2 stream. This is simple a flow splitter where combined flow rate of 20,000 kg per hour is split into 15,000 kg per hour for the solid separation and 5,000 kg per hour in the FSP2 stream. The FSP1 stream is split into SSP1 stream and SSP2 stream. Since this is a substream splitter, it is specified that the SSP1 stream contains 90% of the substream flow rate as of FSP1 stream, whereas the SSP2 stream contains 95% of the flow rate of solid substream. So in other words, 5% of the solid substream is lost into SSP1 stream and 10% of the mixed substream is lost into SSP2 stream. This case study can be closely resembled to the process industry producing a high level of dust, where two different sources of dust are mixed for the downstream processing. Though it's not very clear what should be the solid separation unit, but it can be closely resembled to the cyclone, where 95% of the solid content of the FSP1 stream is separated from the bottom of the cyclone and 10% of the air is lost from the bottom of the cyclone. So let's open Aspen Plus and see how to solve this problem. Let's start a new simulation. Since this example contains solid components for which you have to define the particle size distribution as well, for that purpose either you can go to the category mining and minerals, where a template is provided for the solid components. To start with this template, you can directly open selected template. Alternatively, you can start with the blank simulation without choosing any of the template and fine-tune the requirements for the solid specifications in the simulation file. So let's start a blank simulation without choosing any of the template and see what kind of tunings you have to do to deal with the solid components. Let's first define the components. Aspen Plus has defined air as a separate component. Alternatively, you can choose from nitrogen as well as oxygen as the air components and Al2O3 and carbon graphite. So Al2O3 is the aluminum oxide and simple C is the carbon graphite. In other examples, you can take both of these components as the conventional components, but since in the given example it is said that both of these components as the solid components and their particle size distribution is required, so let's choose these components as the solid components. Let's go to the property method and choose ideal method for this case. Run the properties environment and results for the property environment are available. Let's save this file. Go to the simulation environment. Here you need to do a couple of tweaks to deal with the solid components before defining the flow sheet. Let's go to the setup and see the specifications tab. Here the stream class is defined as the conventional stream, and if you read the details of the conventional substream, that indicates that it's a mixed substream and you can use it when there are no solids in the stream or when only solids present are the salt component. Otherwise, you have to choose between mixed substreams involving the solid components. You can also go to the stream class and do the same selection over here. As you can notice from this stream class options, you can see that there is an option of substream mixed with the non-conventional solids, substream mixed with the conventional solids, substream mixed with the non-conventional solids and the particle size distribution, and substream mixed with the conventional solids along with the particle size distribution. So depending upon the nature of the problem, you can choose between conventional stream class as well as the mixed class having conventional as well as non-conventional solid components, either containing particle size distribution or is there is no information available for the particle size distribution. So let's choose the mixed class with the conventional solids having the particle size distribution. You can confirm the substreams available in the stream class from the stream class section. The available substreams are given on the right side. That indicates that it can handle conventional components which participate in the phase equilibrium, as well as CIPSD class that can handle conventional solids in the solid phase which do not participate in the phase equilibrium but their particle size distribution is available. So by default, this tuning is provided in the default template of solids in the category of mining and minerals. Another tweak that you have to do to define the particle size distribution is the mesh for the particle size distribution. You can define the mesh type. By default, there is a particle size distribution mesh available that ranges from the 0 microns to 200 microns. If this is not appropriate for your case, you can change the mesh by yourself, and for that purpose you can choose between the mesh type of equidistant, geometric and logarithmic. Let's choose the equidistant mesh. Define the lower limits and the upper limits for the mesh size. In the given example, since the particle size is in the micron size and roughly ranges from 0 to 20 microns, so let's define the lower limit as 0 and upper limit as 20 microns. Once the limits are defined, you can create the particle size distribution mesh. Once you are done with this tweaking, then you are ready to go to the flowsheet development and the process simulation. So let's go to the flowsheet section. Either you can define the complete flowsheet once and then specify the streams and the unit operations, or gradually build the flowsheet by specifying the corresponding streams and the unit operations. Since this problem is relatively simple, so let's first completely define the flowsheet and then provide the input specifications. To view the model palette, let's go to the view menu bar and show the model palette. In the given flowsheet, we'll need a mixer. Let's name it as mixer, and a flow splitter. Let's name it as FSplit, and a substream splitter. Let's name it as SSplit. If you are not sure what are the functions of these unit operations, you can hover over the corresponding unit operation and see the details. For example, the flow splitter is used to divide the feed based on the split specified for the outlet streams, and the SSplit is the substream splitter that divide the feed based on the splits specified for each substream. Also, you can read further details about these unit operations in the help. Let's connect the material streams. So all the streams are connected to the required ports of the corresponding unit operations. You can escape the button to get out of the selection. Since the model palette is not required anymore, you can hide the model palette. Also, you can slightly reorganize the flowsheet for the better presentation. For that purpose, you can completely select the flowsheet with the Ctrl A button and then press Ctrl B and Ctrl J. Alternatively, you can go to the modify option and align the complete flowsheet as well as reroute the streams. To further fill the flowsheet to the entire window, let's click Zoom to Fit option. Now you are ready to define the input specifications of this flowsheet. For that purpose, either you can go to the navigation pane and see where the inputs are required. Sometimes it happens that any of the stream is not properly connected with the unit operation. In that case, the flowsheet will not be completed and the status will show flowsheet incomplete. But in this case, the status is required input incomplete. That means the flowsheet is properly drawn and requires inputs for the simulation purpose. So you can notice in the streams folder that 2 feed streams require the specification, and in the block folder 2 blocks require the input specifications including the flow splitter and substream splitter. You can also press the next button or F4 command from your keyboard. It will automatically take to the next input required form. This is the input form for the feed stream F1, where you need to define the inputs according to the degree of freedom of the feed stream. There are 4 degrees of freedom to define any process stream, and that includes the composition of the stream, flow rate of the stream, as well as temperature and pressure. Between temperature and pressure, there is another option of the vapor fraction. In general systems where dew point and bubble point informations are provided, then it's relatively helpful to define the vapor fraction instead of temperature pressure combination. So any one of the parameter between temperature and pressure, and the second parameter can be defined as the vapor fraction. In this case, since temperature is defined as 25 degrees Celsius, pressure is given as 1 bar, and the total flow rate of the feed 1 and the feed 2 are 10,000 kg per hour, and both of the streams have mixed upstream as well as solid substream. The mixed upstream information can be defined in this section, whereas the solid substream information can be defined in the CI solid tab. You can clearly notice the substream name as CIPSD. So let's first define the mixed upstream. The flow rate of the mixed upstream in the feed stream is 99,090 kg per hour, and the composition of the mixed upstream including nitrogen and oxygen. You can define the mole fraction of nitrogen as 0.79 and the mole fraction of oxygen as 0.21. You can notice that even with the definition of the mixed upstream, by default no further information is required for the F1 stream, or if the alumina and carbon are the conventional components without the information of particle size distribution, you can define their composition over here as well. But in the given case, since the particle size distribution of the solid component is provided, that can be only defined in the solid substream named as CIPSD. So let's define the temperature of the solid substream as 25 degrees Celsius, pressure as 1 bar. Either you can define the total flow rate and the mass fraction, both of them, or you can simply define the mass flow rate in the composition tab. Let's define the mass flow rate. The mass flow rate of alumina is 5 as well as the mass flow rate of carbon is 5. And immediately you are asked to define the particle size distribution. Let's expand this option. The particle size distribution can be defined as the exact particle size distribution available from the experimental studies. In that case, you can directly define the weight fractions corresponding to the size of the mesh between lower limit and the upper limit. Otherwise, you can define the particle size distribution as the distribution function. Since we do not have the information about the weight fractions corresponding to the mesh size, so we can associate the particle size distribution with the distribution function. In the F1 stream, it is said that the standard deviation is 2 microns and the D50 are the median value of the particle size is 6 microns. With this information, you can analytically calculate the particle size distribution. Here is the normal distribution of the particle size with the median value as 6 microns and the standard deviation of 2 microns. With this, the specification of F1 stream are complete. You can notice that there is also an option of component attribute on this page. This is particularly relevant if you have the non-conventional components, and for those components you can define the attributes such as proximate analysis, ultimate analysis. So depending upon the selection of the stream class, either that option will appear over here or in the mix substream that option will be active in the component attributes. Similarly, define the inputs of the F2 stream. So the specification of F2 has been defined. So once the streams are defined, you can close these tabs and go to the block option. In the mixer block, by default, no specification is required, but in case the pressure drop or any other pressure for the mixer is available, then you can define it over here. The negative value in the pressure input specification will indicate the pressure drop, and the positive value will indicate the exact pressure of the streams leaving the mixer. Sometimes it may be helpful to define the temperature estimate. This is particularly relevant if mixing different streams results in the enthalpy of mixing. Let's define the flow splitter. In the splitter specification, you can define either the split fraction or the flow rate of any of the stream, or the actual volumetric flow rate, or limit the flow rate, or define the cumulative flow rate, or the residual fraction. In the given problem, it was said that 15,000 kg per mole leaves in the FSP1 stream. So while defining the flow rate in one of the stream, the requirements of the flow splitter are complete. In certain cases, it may be helpful to define the key component as well as stream orders for the split ratios. Let's go to the substream splitter. Here you need to define the specification for each substream. The specification can be provided on the same page or can be defined for both of the substreams. In the given problem, it was said that 90% of the mix substream leaves into SSP1 stream and 10% leaves from the SSP2 stream. So the split fraction of 0.9 as the mix substream fulfills that purpose. For the solid substream, either you can define the split fraction on the same page or you can go to the SSP2 stream. Since 95% of the solids leaves with the SSP2 stream, that means that 5% will leave in the SSP1 stream. So either you can define 0.05 as the split fraction in SSP1, or you can define 0.95 as the split fraction of the solid substream in the SSP2 stream. You can notice that the required inputs are complete and you are ready to run the simulation. Before running the simulation, it is always advised to save the file. To save the file, you can press Ctrl S, or you can save from the quick access toolbar, or you can save from the file option. Let's run the simulation. So the simulation has successfully run and results are available to view. To view the results, let's close the unit operations. In the home menu, you can see the stream summary. You can view the results of all the streams or the boundary streams or only the feed streams, or if there are streams relating the charges or only the product streams. Depending upon the requirements, you can see the results of any of these groups. Alternatively, if you are only concerned to view the results across a certain unit operation, then you can go to the unit operation, right click and see the stream results. On the unit operation, the results option only gives the results corresponding to that unit operation, and the stream results gives the results of the process streams of inlet and outlet from that unit operation. You can also go to the corresponding stream and view the result of the stream, or you can go to the block and see the stream summary of the streams corresponding to that block, or you can also go to the result summary and see the results of the streams. So these are so many different ways to see the results of the unit operations as well as the results of the streams. The most convenient one is to see the results from the stream summary. Let's open the stream summary of all the streams. To better view, let's close the navigation pane Here the results of all the streams involved in the process flow sheet are given. On the stream result summary page, you can notice lots of information about the results of each stream. Let's see what kind of informations are important for this specific example. At the top, you can notice the connections of each stream, the stream class, the temperature pressure conditions, liquid fraction and solid fraction on mole basis as well as on the mass basis. Since this example contains heterogeneous mixture of gas and solids, you can notice the solid fraction of the feed stream. Similarly, the solid fraction in the mix stream is also the same, as well as the solid fraction of the flow splitter is the same, but the solid fractions of the substream splitters is different. Let's view other results. Here are the mass flows of all the streams. The two feed streams contained a mass of 10,000 kg per hour. So the mixed P stream has 20,000 kg per hour, out of which 15,000 kg per hour was sent to the substream splitter, where the streams SSP1 and SSP defined based on the split fraction of the solids and the gases between the two streams. Beside the mixed streams, you can view the results of mixed substream as well as solid substream. Let's view the results of solid substream. Since we have defined that 95% of the solids leave from the bottom of the cyclone and that split ratio correspond to 0.7 kg per hour of the solids leaving from the top of the cyclone and 14.25 kg per hour of the solids leaving from the bottom of the cyclone. It is important to notice the composition of the solid substream in the two streams. You can notice that the composition of the solids in all the streams is the same. So the substream splitter only splits the substreams between different streams without altering the composition of each stream. This means that regardless of the nature of the solid components, the SSplit has simply divided the solids between SSP1 and SSP2 streams. Otherwise, for practical application, it's might possible that the individual physical properties of the components play a critical role for their separation, even having the same particle size distribution. Similarly, you can also notice the particle size distribution of all the streams, and you can notice that mixer, flow splitter and the substream splitter all results into the same particle size distribution. For a physical unit involving separation between the gas and the solid, as in case of the cyclone, the particle size distribution of these two streams should have been different. The solids leaving from the bottom of the cyclone should contain the particles having higher micron size compared to the solids leaving from the top of the cyclone. So this SSplit unit is simply a theoretical unit and it shouldn't be considered as a physical unit for reliable results. For practical application considering gas-solid separation, you are advised to choose a solid separator based on the physical operation of the heterogeneous separation between solid and the gas. You might also be interested to see the concentration of solid components in the SSP1 and SSP2 streams. Any of the other property that is not available in the default result summary page, you can go to the add properties and search the required property from this page. Let's see what are the concentrations of the solids in each of the stream. For that purpose, you can simply choose the mass concentration component option, click OK. It will add the desired property in the components. So close the substreams and view the results from the mix stream. Here are the mass concentration of the components. Let's see what are the concentrations in units of milligram per cubic meter, because that indicates whether the air is breathable and inhalable. You can notice that the concentration of solid components in the feed streams, outlets of the flow splitters are more than 582 milligram per cubic meter, whereas the concentration of SSP1 stream that is leaving from the top of the substream splitter is 32.36 milligram per cubic meter. That is reasonably close to the solid concentration for breathable air. The concentration of solids in the SSP2 stream leaving from the bottom of the substream splitter is significantly high compared to the stream leaving from the top. So this is how you can view the result summary and interpret whether the results are reasonably reliable and correspond to the physical operation of the chemical process. If you want to view the results on the top of the streams, go to the modify option and check the relevant option from temperature, pressure and the mass flow rate. So that will represent all of these results directly on the flow sheet. So in this video we have learned how to define the specification of a process stream. Also we have learned how to simulate a mixer, flow splitter and the substream splitter. In the next video we will thoroughly cover separator model palette with a specific emphasis on the 2-phase fly separator, 3-phase fly separator and the decanter.